introduced like, swell of phenotypes quite well. So I'm just going to introduce quickly where we come from and how we set up our data acquisition, some of the things we've had to think about as we look at our data handling. So I actually think I'll come to a slightly different conclusion as well. So National Phenome Centre, we're a collaboration between the MRC and the NIHR, obviously coming out of the old Olympic drug testing facility. In all honesty, there's very little of that in the NPC, but it makes for a good story. So we've got a lab at Imperial College, unfortunately split across 2 sites. So we have NMR in South Kensington and a mass spectrometry lab in Hammersmith Hospital, and that's something that's actually become quite significant to us. And we're designed to, there's a goal to expand the work that we do to other centres within the UK and around the world. So we've made the decision in the NPC to be very focused on what we do. So we deal exclusively with human live fluids, so that's blood and urine, nothing else. And we follow a very, very standardised workflow. So we deal with, let's see, NMR. We always run NMR on all our samples. So we generate our typical assays, so sort of 1D profiles, spin echoes when you have plasma samples in order to get rid of some of the lipoprotein resonances. And we also do J-resolve spectroscopy in order to find some grist for our identification pipeline. Now, I think anyone who's familiar with metabolic profiling knows that this is not significant data, so we'll just leave it aside for the rest of this presentation. On the mass spectrometry side, we run one common assay between urine and plasma, which is the HILIC small polar molecule detection. And then depending on whether we're looking at blood products or urine, we'll either do a lipid-specific assay or a reverse phase assay. And this is just for technical reasons, but they're both your typical broad spectrum sort of profiling MS assay. So we run our samples, we run a very strict 15-minute cycle for our acquisitions, and this is to keep one day's acquisitions to 96 samples fixed on a 96 well plate. It means we can keep a very rigorous sort of put the samples on at X o'clock one day, it'll be done in time for the next day, we don't end up with this sample creep that some of them come in at 2 in the morning and you'll just change the plate. So our typical assay generates about 8 gigs of data in the continuum mode assay. If we centroid that, obviously we get down to a much smaller data set, approximately a gigabyte. And if we try and, we're interested in converting that to some of the open formats, which is obviously quite useful, we then actually get a large amount of inflation. So MZML, we expect a small degree of inflation, but actually we more than double the size of our assays if we convert to MZML. And MZ5, we get improvements because it's a binary format, but it's still inflating things. So, Christoph, Jeremy likes to talk about petabytes and petabytes of data. I'd like to be a little bit more conservative. So if we take 8 gigabytes every 15 minutes by 10 instruments, and let's say the spectrometer works about half the time, I think that's a reasonable estimate over the course of a year. That's about 1.5 petabytes a year. Or for a typical study, we look at about 2,000 samples. We're talking about 60 terabytes of raw data. And at the moment, I'm still continuing. So that's, if we assume all the instruments are working at one time, that's 7 terabytes a day, or 10.72 gigabits a second. So that's actually a large proportion of all the bandwidth we get over a gigabit. Now, obviously, almost no one uses gigabit purely these days. So we have this situation where we have individual gigabit links from one instrument down to the main switch in each building, and then 10 gigabytes switches down to the data center in South Kensington Borough. So in all, we're not saturating any kind of bandwidth. But one thing we have to consider is if we were to start, say, throwing in converted MZML data sets, we're actually going to get to something that doesn't saturate a 10 gig link, but getting up to maybe 20%. I think that's enough that our ICT department start paying attention, especially as we're now basically filled out the Eng data center at Imperial College. We've got no space in South Kensington. And so most of our future expansion is going to take place in a rented data center in Slough. So we're pushing all of that out across Janus as well. And So reducing the data here is critical to not causing trouble down at this end. So first question is, why are you dealing with continuum data? Because the first thing we can obviously do is go straight down to centroiding when it comes to data reduction. And unfortunately, we find that there are significant quality problems with just going straight to centroided data. One of the prime ones for us is we deal with spectrometers, all TOFs, and what we find is we like to tune our TOFs for sensitivity, because when you're running very long assays, we find that sensitivity is something we can trade off against the length of the run. Unfortunately, it's a kind of inherent attribute of a TOF that when you look at the resolution, it's actually, resolution is dependent on the intensity of the peak you're looking at. And so most peaks we find down at the tails, the top of the 10, bottom of them, they're significantly broader. And this means the centroiding algorithms tend to fall over, and we end up with these funny little split peaks and so we end up with little fragmented centroids at either end of what should be a large unified peak. And that brings in further noise in the peak picking. I mean, we're all used to the idea that we've got thousands of peaks in a mass spec profiling data set. As you dive down, there's still thousands under here. The problem is obviously distinguishing signal from noise. And what I would contend is that actually we don't have a problem with data size metabolic profiling. Actual metabolic profiles, a set of MZ retention time tuples, that's enough to reasonably specifically identify a compound, or even just the actual chemical identity and intensity. That's no data at all, even like tens of thousands of data sets. The problem is that the process of going from continuum mode to centroided to a set of peaks and integrated values is so open. There are so many different ways of doing it that we always end up needing to retain this original data. So for my mind, the problem is that we need to tie down this process of coming from raw analytical data to peak pick data, either by finding a set of standards that allow people to reproducibly and reliably do it, or finding a better way to do it. So just as a way of presenting this, I've used 3 common peak picking tools here to peak pick one single data set. And so we have intensity, retention, and mass. So in blue we have XCMS, I imagine a lot of you guys use this. Green we have the grid mesh algorithm out of MZMI, and then in red we have the Progenesis QI, which is the peak picking software we use in-house. And you can see we've got all sorts of differences here. So initially, XCMS and QI both give far more peaks than grid mass. And you can see QI actually has a systematic intensity difference, which is probably just a baseline offset, but it's still interesting when it comes through. This is just zooming in on this so you can see where people picking agrees with each other and all these things which are much more idiosyncratic. And no one's got the time to go through and individually say, it's this noise, it's this signal. We need a way of more efficiently filtering all these things out. So I think authors here have some interesting work on the continuum mode data set, but that's all I wanted to introduce you to.
Thanks, and probably forgot to say that this is supposed to be a highly interactive workshop. Actually, less presentations than actually talking and looking into problems. So this is open for discussion. One question that I immediately have, you already pointed out. I mean, obviously we can't convince funders to fund our lab projects with the numbers that you absolutely came up with. So we need to stick with the megabytes and exabytes, etc. And I actually think it's one of the big questions is, do we need to keep the data from the earliest time points of the acquisition, because there will be
I think it depends on the context of work. Right now, the field of peak picking is still in some flux. I think it's crazy to throw away data. There's no telling we won't get there in 2 years' time and be able to find something much more interesting and just get more reliable information in data sets. There are also contexts such as clinical trials where retaining raw data is benefited, so you can't get away with throwing away this information. But I think in a lot of cases, going forwards, no one's going to want to see a chromatogram from a 10-year-old who experiments. I think we need to find ways of better summarising this information and better allowing people to judge the quality of the data set without looking at raw data. I think that's one of the big gaps at the moment. It's very difficult to say if data is good or not.
Wondering, it's probably silly for me to ask you this question since your office is like 3 doors from us. But anyway, I just wondered if you had tried any standard compression algorithms on the either continuum or centroid data and how much compression factor you can get out of it.
So zipping up the continuum of data you get maybe a 20% reduction. So it's significant. One of the problems we have with all of these conversions is there's a tendency to want to move your data centrally, then do the conversion, which actually I think is a very inefficient way of doing it. To my mind, it's not ambitious. We want to convert data sets to different formats. Do that on the instant with a modern computer. It's pretty much idle the entire time it's acquiring data. So there's no reason not to be doing data conversion on those levels, centralizing all that data. Now, the problem when you look at something like MZML is obviously you have continuum data and a massive information ML from. Start getting to that where you're pushing it out back. So
presumably, MZML being a massive format, you can compress that with standards of algorithms, get quite a lot of that back.
It's not strictly massive because all the actual intensity data is kind of like a index or something like that. So probably isn't as we agree.
So do you think that the sort of standard compression algorithms are not going up?
I would argue that there's a lot in the data set that we can afford to throw away. So I would say that when you look at all this, there's a lot of noise in the end. I've actually shuffled it to the end, but because I didn't want to skip right past it. Certainly in this TOF data, I think there's a lot of information that we can afford to throw away and still have a perfectly good data set. And actually, I've been doing some work with Kieran and Richard. I emailed Kieran and Richard doesn't but they've been doing some very interesting work on finding out what you can actually scrape out of these data files. Can you show me anything? Okay.
That's perfect. That's what we.
But there's certainly the case that you can remove a lot of information from these data files, still keep everything interesting, and easily cut the data size or keep the data set down to 10.
But that's also dependent on the peak thing you were saying, that maybe in 2 years' time there might be a more sophisticated way of peak picking.
That's true, but one thing I would argue, and I think one problem we all face in profiling is, if you're doing untargeted profiling, you have to be able to put a name to what you find. I mean, you always have to be able to put a name to what you find, or you're just going to be very disappointed the whole time. If you peep it down to the noise level, and you find something down in the noise, are you convinced that you could then identify that? I think in a lot of cases, without a huge amount of work, you're just going to be sitting there going, sorry, it's too small. Without wanting to see, I was going to say chicken, but that's not the right phrase. I think it's much better to work at a high level, cut out all the very lowest things and say, we're confident that these are all well above our limits of detection. We would be able to identify them should they become significant. It's kind of
No, I agree with that point of view, and it's a similar to retail. But I also am wondering if that in the future there will be people working on new ways to do that peak picking, make it possible to work with this type of data.
Absolutely.
But why would they go back maybe at that stage? You know, we're running 100,000 samples, nothing already, and then with those samples and not too bother to go back to the samples we're right now. But
I mean, I'd say that I don't think, the likelihood of people going back is small. also the kind of things we talk about removing denoising out is nothing that even a trained spectroscopist would tend to think was. So these are the kind of little transient blips that if you look at that across an entire sample data, you'll see enough noise in one place where most people are able to go, oh, maybe something here, and turn it into when an actual analyst comes back to look at this, they'll go, it's nothing. But by that point, it's too late to pass that through.
So in this, I think in this whole workshop, we need to make a case distinction between different scenarios. A center like yours following specific scientific projects will have very different requirements than, for example, a data provider like EBI who archives data over decades, for example. In some areas, we have to throw away data from early phases of communities coming up, but in other cases, we really archive data over a long period of time. We cannot envision the reuse, the types of reuses for data that scientists will come up in 5 to 10 years. It's very dangerous to make assumptions about this. So just for people to keep in mind that there are these distinctions in the application scenarios. Profit sets that the individual communities compensate that. And so, yeah,
can I just ask, and this is someone coming from outside this domain, I don't know at all much about the data type and methods, but it strikes me that there's an abstraction, so there's a computational process that takes you from continuum to a peak data set. Absolutely. It's big data reduction. But there's heterogeneity in the methods that are available. No one's finalized what necessarily good is, or there are genuine reasons for difference. At the same time, there'll be different platforms, technical platforms, behave slightly differently. And there'll also be different operators in those platforms. There could be the level of the centers that are providing running these things, or it could be a level of individual labs. So in terms of the abstracted output, so peaks that you get through the different analytical processes, is the variation between those outputs greater or lesser, or the same as the variation you get when you have different operators or different back-end vendor platforms?
It's an excellent question. So to roll back, to start off, we'll talk about the noise. I think most people are aware of the axiom that trap-based mass spectrometers, all the traps are give you less noise than say a top. I don't think that's strictly true. The instrument vendor there has made the decision to present less of that noise to you. So that's something that is presented as inherent in the platform. Actually, it's a decision that we made by a software vendor. In terms of what drives the variability, operator or platform, I'd say operator is almost indistinguishable from that. The problem with all of these technologies is because you are sticking the sample in fluidics, you're always going to see variation, sort of longitudinal variation. That's easy enough to disentangle when you're doing sort of one continuous run, but when you stop, it's very difficult to join that tail back on. If you were to stop with one on one instrument and start on another instrument, again, it's very hard to say, okay, am I seeing a continuation of the same drift? Well, no, because now you've got clean instruments, new column, etc. And so, I mean, in our experience, we run sort of almost 20% reference samples when we do our analyses. So for every 8 study samples, every 8 biological samples, we'll run 2 references. And we see CV, so coefficients of variation on individual peaks of anywhere between 5 and 30%. And we take 30% as not a good CV, but just about acceptable. Obviously a huge amount of noise that's way beyond that. I think comparing operator to operator, it's more likely that's instrumental variation that I couldn't answer you.
Definitely there is an operator or processing variation of
absolutely, but the degree of the magnitude of the two is almost impossible to answer now.
It is, so I mean, it's pretty obvious why I'm raising it. When thinking about focusing, this is a challenge that hits the computational domain. protocol that we use in the computational domain. It's important, I think, not to recognise that there could be other areas of the whole process, from the experimental system, the sample taking through the assay, through the computational analysis, that may actually change the dynamic of the whole thing in terms of things like data reduction. I mean, it's very interesting that you said that one of the vendors has made a decision about reducing or not exposing a certain part of the noise profile, whereas other vendors haven't decided. Those kind of things really, they play a very important part in how you plan out what you do downstream. So anyway, it's interesting to think about this as a whole flow that starts with the capsule and maybe not directly focused just on the data.
And that is very much a package. You have to be, I think, very careful not to premature doctor and not say, first off, you should concerned with the idea of just throwing everything away too early. I've never advocated. You need to keep enough information that you can trace down where the source of the variability are. But I do think that things like baseline noise are beyond the scope of most of our analysis. Most people would, as an educated, say, analyst, look at the spectrum and say, this is not, that is just happenstance that a particular signal vector at that point in time is safe to flow.
Got a really high signal, how much confidence? I think that's something biomarker sees that is how much confidence.
Exactly. That is very difficult to just a signal. I think people do like to think that if they just share the data set on that holy grail thing or something like that, in all honesty, it's not.
Okay. So I've just been alerted by Ronan that I forgot one of the most important parts of such a meeting, which is round table introduction of everybody. And I think we will just do that now. Maybe we can start with it.
Hello everyone, I'm Richard Chapman. I work for the Corporation in the Research Department. I'm newly transferred in, so I've only been in the Research Department a week, so you have to pretend to be one. This is my first conference, so this is all workshop or anything outside of water really, so it's all very interesting. I am interested in the data compression things across the board from mass spectrometry, but also particularly for imaging. So if anyone wants to talk to me about that, I was previously in charge of the instrument control department of waters, so I'm familiar with the problems that take. Again, if you've got some problems where you've got an instrumentation, there is a fun one. You're going to do all that. It's all the data. So, yeah, it's good to be here. Thank you.
Yeah, I'm Kieran Leeson. I'm a business analyst at Board. Primarily sensors. So I've been last 12 months working and more recently focused on imaging product roadmap, so Metabolomics, Metabolomics programs and that as well.
I'm Rob Faber, based in Birmingham. I'm by petition with Mark White and also involved in the imaging. Also from Birmingham, involved in Genome Centre, Genome Centre, or not one,
I'm Tim Emeralds. I'm at College. I'm really complicated bioinformatics and been helping for a long time. I'm sort of very peripherally involved but I'm interested in data mechanics.
Vanessa, software developer here at DPI. My name is Jonathan Escaino. I'm associate been involving computational mass spectrometry for a few years ago. And I'm also involved in Metabolomics projects. That's also my and also other people here are also agreeing to many of the data standards that are used now in the
Chris Sandick, leading the chemical kinetics and metabolism team here at EPI. Also PI of the Cosmos project for coordination of standards in the rooms and PI of the Phenomenal project, which is talking about.
Jake Pierce, I'm managing the informatics arm of the Phenome Centre at Imperial College.
I'm Gonçalo Correia, I'm a PhD student at Imperial, and part of my project I've been analyzing immunological data sets which usually tend to be a bit bigger, and that's why I came also to some issues.
This is Valley, metabolites, and mostly all the data and so the GH metabolomics side of
Hello, Stephen. Also part of Metabolomics. We'll be doing some software engineering and looking at integrating data analytics.
Hi, I'm Stanley. I'm from Medical Research Council in Nutrition Research. I work inside Albert and I'm an investigative scientist. I'm recently made the transition away from being lab-based chemists to computation chemists. I'm really interested in recovery and the assignment of the my main interest is science.
I'm Bob Gorham, I work at commercialization now. I set up the Metabolomics lab there, and been involved in quite a number of large scale studies, looking at lipid profiling, generating reasonable amounts of data, and also being interested in the work of project.
So I'm Guy Cochran from the European Biometrics Institute here, and I look after sequence data repositories and services that sit around those repositories here at EPI. So, before, as Chris mentioned, it's a different data domain, but we maybe have some of the community and social sides to data production.
My name is Michael Conklin. I'm from Holland. I work in the group of Thomas Ankermeyer, where I'm a software developer. I'm also involved in the Cosmos project. In NIDA, we have a pretty nice lab set up, a lot of mass spectrometers. That's the reason why I'm here. But I'm also the maintainer and creator of Metabolomics Exchange, which is an aggregating data sets like metabolites.
I'm Arms Lucas. I work currently designing Delphi, but I used to work on enterprise pipeline development. I'm also interested in the data storage improvements and data.
I'm Andrew Dowsey. We're in the Electrical Engineering Electronics Department in Liverpool University. We do signal processing and statistical algorithms for mass spectrometry data, including data compression and new centroiding and noise reduction.
Hi, I'm Chandu. I'm a software developer here in Metabolites. Right now I'm working on pipeline development for the Metabolomics data.
Yeah, I'm Ken Howe. I'm in charge of the Metabolites database. I work for Chris. And not particularly concerned at the moment over data sizes, but we have been told from higher up that we should be concerned, so I guess it will happen. Since am I the only one who's warm? Is it getting quite warm in there? I'm thinking quite stuffy over in this part. Is it cold over there?
It's just a question.
Yeah.
But here online as well. Here online, anyone? You want to introduce yourself? Is that online or?
I did the data from here in Canada, so here to learn more about the challenges.
Quite smaller data set.
Thank you.
and I'm designing new data formats, and I'm also interested in reducing the amount of data we write in the future.
Thank you. Robert, can you repeat that? It's a bit low sound at the beginning.
My name is Robert. So I'm coming from ICANN, and we are doing software, mass spectrometry software, and mass spec database. So we are creating mass function software and MD4 database.
I guess that's it. Yeah, so then we can continue with our program. Keyboard is so hard to. Rick, you need to press escape or something like that. When you come back in, you need the download.
Have you downloaded them all?
Yes, there is a, you go not the download, but you go to the link that you will download. We need to download. Yes, I copy the screen from the line. Yes, thank you.
Actually, a lot of what I'm going to say has already been said by Jake, so I will flip through quite quickly. This is University of Birmingham Metabolomics presentation, actually. So it's Ralph, myself here, Mark as well. So really, just to give a quick introduction to Birmingham, we've got both MS and MR facilities. We've got a new Centre of Computational Biology, centre there, which has a focus more on genomics, but it's also integrating with the other omics as well. It's going to be part of that metabolomics focus within there. And then we have two large facilities, the Phenome Centre Birmingham, which will be up and running by the end of the year. We have a lab now, as of this week. And then there's the older metabolomics facility, the Birmingham facility, which is NERC funded, which Mark directs within there. So we've got data, different aspects, both mass spec and NMR data going in different applications as well. Give an idea about the number of analyses per year. So we're not up to the level of the National Phenome Centre. We won't be with the instrumentation we've got. But Basically, the NERC facility is doing about 2,000 to 3,000 analyses per year, mass spectrometry-based analyses within there, both direct infusion, mass spectrometry, and LCMS. And then the new Phenome Centre Birmingham is going to be up to about 40,000 mass spec analyses per year, and there's got tendency to come into there. So still quite a lot, but like scales that we've heard of in the last 2 years. And these are just our typical workflows. I think it makes us think about where. I personally think that around want to come in here as well. We just need to do the level of data compression or reduction within there. It's what stage that performed within there. So we're performing reverse data very similar to the National Phenome Centre there for the LCMS and the blue. We're collecting in profile continuum mode, how we like to call it, both mass spec and MSMS data as well. Obviously, the MSMS data is much less data intensive than the full-scale data within there. You heard about reductions in noise. Well, Thermo is one of those companies that do that. Okay, so Thermo file sizes are a lot smaller than there's pros and cons obviously to that. We apply XCMS data, raw data processing, and then typically that comes down to the gigabyte file. We're using ProtoWizard to convert into ZML before we go into data analysis in there. Then the SimStitch, which Ralph knows a lot more about than I do, basically one analysis, one sample, which is 3 records in there, with about 10 gigabytes of file size. And then in-house production, in-house data processing, which that's there. So you're going from very large files to very small files. So this is what we're doing at the moment. So this doesn't include Phenome sensors, just for the limited number of instruments that we've got. We're taking about 28 terabytes per year. If we store all of that raw data, is all the raw data stored, or is it?
Most of it depends. We have different, for example, FTSR, we've got 4 changing data as well. That is so that we get rid of it. So that's just one.
But that's because of file size as well. So it's been the decision within Birmingham to do that step. So I think it's something that we potentially need to be suggesting for this workshop. We go on to, this is what we expect or what we plan. This is total per year. Okay, so we're going up to about 200 terabytes per year within the next couple of years. So again, relatively large levels within there. So we've got infrastructure at the moment within Birmingham to be able to cope with that to an extent. I'm very interested in profile and central data acquisition. Something I've been involved with for a while, but I'd like to look at more to see. A top and an Orbitrap system is very different. The type of data you get from that is very different. How efficient can you be in converting from profile continuum down to central data? How much data you get out there? And that's something we've looked at. We've looked at a lot specifically top data. Orbitrap data is very different because of something else being reduced. But that post-data acquisition processing might be important way to go. The conversion. We're doing post-data acquisition. We are converting central data or converting via to XML format. We are storing data, basically raw data in central mode. We do some data storage in there. That's a secure mode. But this does need further research to make that something that this workshop. Another thing we're doing in Birmingham is something called deep metabolome annotation. This has come out primarily from Mark Vine's group. And so Thermo Fisher Scientific heavily involved in this. Robert, who's on the line, Robert Mistrick is also heavily involved in this as well. So this is where we're taking one sample type, doing significant fractionation of that sample, and then collecting both LCMS data on different SPE fractions, biphasic extraction, sample extractions within there, and then collecting MSN data for all of those fractions until hopefully the majority of the metabolites are in each of those fractions within there. And we're currently expecting, that we don't know, because we've not got this far yet, expecting up to about 10 terabytes for any given sample data. So that's again for us to go on and do multiple sample types, and that's going to be quite important. So just a summary, so at Birmingham we expect about 200 terabytes per year. Raw and processed data that we need to store. That's within 3 years. I'm interested in looking at the profile as a central transition, see whether that's the way to reduce data down, test data down. The analytical strategy, so we've already mentioned mass spectral imaging, it's not something we're doing at the moment, but obviously that's really, really important. Obviously, because you're having involved in that as well. Just two very quick things. We require a single community agreed solution. I think we all agree here that that's required. We want to be applying the same process throughout. And really, storage client, which features of the data, when we decide what we want to do or what we describe that we should be doing, we want to be thinking about what we're going to be doing with the data for the next 5, 10, 15, 20 years, put in there, how the data will be used, what we want to use it for, because that will really drive at the top threshold reduction. Without deciding that, then it's difficult to come up with one solution for that. That's it. Any questions? Thanks.
It seems that all the mass spectra are from the same vendor. Is that your case as well?
The Phenome Centre Birmingham, there'll be instruments from Waters and from Thermo. It's basically 50-50 split. And they are very, not so very different, but they are different data sets with more data essentially. So how you apply something to one data set, and one instrument, or one manufactured instrument, isn't necessarily the same as what you would do with a different data set. And that's one to consider as well.
So can I ask, how long do these machines last? Do they get replaced every year or every 5 years?
No, well, we typically say an instrument should last 7 years. Technology is running along very, very quickly. Okay, so the Phenome Centre Birmingham, they will be there for at least 7 years.
Right, and are there updates to the chemistry or the so within the same machine? Does somebody come along and do something that makes it more productive? Or?
You can get upgrades, yeah, on instruments, but I think it's more important within the Phenome Centre is that we're collecting equivalent data when it's on day 1 or day 700. That's the important thing, making sure it's reproducible so you can that data time frame. So, for example, in the Phenome Centre Birmingham, we'll be making sure we're getting reproducible data. We won't be trying to run it and try and measure everything or more. We're just trying to make sure it's reproducible.
I mean, comparable data.
Yes, yeah.
But do things like throughput and speed and time to clean up and to fix things for the next one, do they change over time?
No, you shouldn't do unless there's a big problem with the instrument. That's what it started with.
Yeah. So I'm just trying to get a feel. So right at the end of this, there's this big growth, this big exponential growth of data arriving in EDR. So is that growing at that rate because of the fact that more people are doing it and there are more centres setting themselves up, or is it growing because the technology is being, the new technology is being developed and it's being rolled out such that a given machine can do much more for the same amount of operating time?
There's step changes in instruments every now and then, but it's more that, I mean, this year there's only 1,000 people at the Metabolomics Society Conference. The previous record was 700, so there's more and more people coming into Metabolomics, there's more and more users of what is coming out there. There's more and more groups being set up, being just set up to do Metabolomics.
So isn't it also becoming more popular to share your data in information like Metabolomics?
Yeah, I totally agree with that. Yeah, both from the journal's point of view, but also within the community, there is a generally good recommendation to share or want to share data.
But I think it's also that people are more confident with the methods and are. Yeah. When 5 years ago, people would say some sort of 1,000 was used on taking. Well, now people, 50,000 samples. That's very so that's probably more values of data coming from than changes in the technology.
Like big groups, of you can count on 2 hands.
Yeah, I think the step change or the difference between, say, sequencing is sequence always tends to just, at the end, you just get the sequences faster. Whereas new instrumentation, is more sensitive, so you will see more as time progresses. More deeper into potential exponent profile. But I think that's a relatively small contribution compared to just the general increase in size of the field.
Yeah, I think it's increasing the size of the field. So the people who call themselves metabolomists, that's the word, or do metabolomics, more of them. There's also a whole other community of people out there in epidemiology and biology in general who become users of technology. So particularly things like the Phenome Centre, other facilities are being planned all over the world. You hear about them, whether they're aimed at epidemiology or smaller scale things. So there's much more of that being
funding about as well as when you look at states. In the States, for example, the research course, that's one example. I mean, that's why I think there was, that's society in San Francisco.
These are a small portion of data shared as well. I mean, if say 100 public data sets and
2,500,
and then that's the same data science paper. It's about 1% of estimated data producers and data shares. It's a very small portion. If you put US at maybe 2% or 3%, still compared to sequencing, which is commonly you can't publish in that share. In metabolomics, 90% of the time is not the case. So if that is too much already, if everyone shares at a 90% rate, that's already a huge statement.
The normal journals in the next 5 years will be wanted to have it publicly available, or funders will have to.
That's one of the big problems is they want to mandate that now. We couldn't do it.
That's why you get the right setting that which is the standard or how to deal with it. A big solution will be etc. But now leading to the question I had from your slide, a single standard, not multiple standard. What in the context of what does it mean?
Well, think about MZML and MZXL, how they came in.
So is that just a data form?
Yeah, well, it could be anything, yes. That's what
Because I thought there's a sort of flavor of instruments that a single solution may not be working. So if you call that a standard, then it's a multiple standard.
Yes, yes. I agree with that.
To get back to the technical side of things, you're running the central idea you're looking at is the obvious reason. Is that just because you wanted to have the continuum rate density there, or find you get better results?
If you don't find we necessarily get better results, we're totally thermo at the moment, so on those systems we don't get better results. Or worse results. So we are detecting the continuum rate not necessarily with the
Okay, online question.
Sleep.
It's a lot of noise.
Okay.
The speakers.
Yeah, so I just wanted to say that so when people are studying MCX and that's few, that's so MCML is the one that was agreed as I'm pretty sure that MCXML will be used less and less because also it has a lot of problems for extending it. So I think that the problem of having just one standard format for data will be solved in this way. But there are other formats that are not considered to be standard, but they have been developed by other people because MCML cannot fulfill all the needs from because we need to access to the data in a particular way. Of course, XML way is very inefficient. But MCXML, I'm sure it will die. So it will, of course, it's still widely used because it was used for many years. But this is the trend.
This reminds me of that question I had about to ask, but at the end, the performance community did a comparison with the compression method on the XML. So that's the file sizes, the 1K presented that goes up to 268% when you convert it and then to 158%. The compression routine went back as even better by combining different algorithms. I think that plus and it went really substantially lower even than it's a lot of dependency, right? It's a tough thing to the data and the platform. Even they try hard.
Present some of that to bother.
Are there any initiatives to get rid of the XML format and more efficient format?
So as I said,
okay, that's cool. Yeah. Like HTML.
The rest.
Well, it's the same story as previous two speakers, I'm afraid. At ASMR, we've been working on lipid profiling for several years now, where we're interested to use metabolite as a profile and lipid phenotype, especially to work together with ongoing projects in the Cambridge area on genome-wide association studies. That's all focused on developing fast methods to be able to run these very large sample sets. Although when you run, I'll be talking mainly about data on samples, with every analysis of the sample according to what we're running QCs and blanks to maintain a full process. And that, of course, is also a certain amount of the total data that we produce. So about 25% of the data we produce is actually just quality control and blank data, which is for the end users not that interesting, but for people who are interested in using the data and mining the data, of course, crucial to be able to see which signals are real signals, which ones are background or so the first big projects we started using this GC, and like I think Jake mentioned, NMR. This is a type of technology that doesn't produce much data compared to the mass spec machines, especially because we use just flame ionization techniques. And we're measuring about 30 compounds in one run, but we do it on a very large scale. So it's about 20K per sample. But then the total results file, 50,000 people, is about 70 megabytes. So that's all very small. There's no issue with data whatsoever in the area. Then we're doing targeted metabolomics, for instance, with the biography kit. And it's a bit similar, although instead of looking at one trace, now we're looking at 185 traces. But again, running that on larger sample sets, like 10,000, 11,000 samples, the amount of data produced in that is really small, like 50 gigabytes of total data, and the result file is about 40 megabytes. That's all easily doable on standard platform. But the other part of our work is all focused on orbit traps, getting high resolution data, and then things go much faster. So the method we're using is direct infusion mass spectrometry, which at least saves us the problem of deep picking in the chromatographic domain. And it has the advantage that it's quick, so we can run a lot of samples through that. So this slide is still 9 to 12 plates, but we usually switch over to 3 and 4 plates. So that we can run very large studies. But the bottleneck there is not so much data storage, but also the processing of the data, and which peaks you get out, and what algorithm to use, especially when you work on sample sets which are larger than say 2,000 or 3,000 samples. The original first big, what we thought was a big study at that stage, was 1,500 samples. There was about several gigabytes of data, but we ran into the problem which was already mentioned by Rick. You have to inflate the data by moving it over to MTXML to be able to use other types of software to be able to use deep picking like XCMS. And the time to do the deep picking is actually where, for us, it's a big bottleneck. So when we moved over to the second study, we had to use a new approach or a different approach for deep picking, where we just compare it to a list of standard lipids, because that saves us the problem of using the alignment approaches in XCMS. And then we can multi-core as well, multi-thread that data processing as well, so the next one much quicker. But still, the data, what comes out of it is all, the results files are quite small compared to the original data file. So the big result file of the whole study is smaller than the data file of one sample. So that's the amount of room we have to think about data compression. And now we're running a sample study called Interval, which is 50,000 samples. So at a speed of about 1,000 samples a week. And there we really have to see where we get with the data. The right and try to think of that beforehand to see how that will work. But again, I assume that with the technology we have in place, we'll still be able to run it, but it will be about as big as we can get. So then imaging is, we're doing not a huge amount of imaging, but imaging mass spectrometry on a high resolution instrument produces a huge amount of data, but luckily it's quite a slow method anyway. So we're running, say, 400 samples a day through the direct infusion, just imaging 2x2 centimeter slide. Will take a whole month. Maybe it produces a gigabyte of data. The total amount of data generated by the instrument is not a huge problem. But just about a week ago, we've got excellent Qtop with iMobility. And that's a type of instrument that about a gigabyte per half hour. And as we've just got the instrument in, we haven't really looked at it, how we want to use it and what we can do with it. But that's the first instrument from outside that really got me worried about data. And how we're going to store it and how we're going to keep it. That's just a huge amount of data that the instrument generates.
It's only for half an hour per day.
What?
Only limited half an hour per day.
Well, per day, yes. Yeah. Well, I think that with every mass spec, you would say to people, run a sample and then first figure out what it means before you start running the next sample. Then nobody will have this problem.
First of all, I think it's very useful to see that all of you guys have the same story. So that makes it much easier to write your story.
Yes. Yeah, that's true. Yeah.
Any other remarks?
This topic? I was just going to say, I mean, the 50,000 sample study.
Yeah.
Even though like the fancy fingerprints. Do you think you'll be getting more similar sized studies in the future after that?
Yes.
So that's not a blip.
No. I think even this study, we're only measuring the baseline sample, but there are follow-ups as well.
So I mean, you'll agree that it's animal.
Yeah. But we only use one method, so we only do the direct infusion. And it's only 2 minute analysis.
So, obviously, slightly related to this, are you moving towards some limit solution to make sure that all the data is tagged and annotated with metadata at the earliest possible time point? Do they have something in place?
Been in discussions about our limit system.
Oh, yeah. So, yeah.
It's ongoing.
I think I had an exchange with James and Jules about this.
Yeah. The lens we're using is very simple, I think. But it's the bare minimum to be able to get track samples and know where very much an ad hoc per project approach. It's not a limb system or limb solution throughout the lab.
Before we have our discussions to get a system for our whole unit. This is what happens now. We'll regularly try to find until we know what they're doing. But that's something we definitely want to.
Yes, it's always been.
Because
if you have everything in good shape, then it makes it much easier to move data around and later find it again. And
Oh yeah, that's no issue. Yeah, that's all we do. Yeah. Although it's not an official limb system, that's all in place.
I have a general question, and coming from your slides, which is very intriguing, that 25% roughly saying that it contains using lines, reference, compound, anything else. So this will be a general question, and as well as to you, Albert. If you want to keep a study, because that's like quite a lot of extra data to keep, only as big as the entire study, but something around 20%, 10% to 25%. Is it? But I guess my understanding is this data is you want this data to check if it's that, so it can't be thrown away. So that's quite a big percentage of potentially.
It really depends what you want to do with the data. What you want to do with the data. So if you want to store the raw data, then and you want to do something with it, you will need all that raw data with it as well. If you're only interested in the results, so if you're a non-mass spec person, if you're interested in the results, then you're only interested in the results table, but even in there you would like to see. If you're a bit analytical, like that.
I think it's all wrapped up in this question. Will there be better processing methods in the future? Probably there will. And the difficulty of predicting that. So, something like UC data is quite easily be involved in utilised by that method. Then that information could be subtracted.
I think the only way you could consider cutting out the QC is when you have that aspect.
Yeah. If somebody invents an aspect that is perfectly stable, always gives you the right answer. Yeah, that's a long way.
Checking the narrative and then some of these species, otherwise you can't really put the studies together.
I mean, really, the way I look at it, even the actual studies sometimes are good ahead, but it's better. It's one of the things that you have actually been asked them to share it, because by default people don't share those things. They only share this is my raw data. But don't want my QC. But if people are uploading from satellites, not. By default, if they're not prompted, not necessarily share this data, because they think I already spending a long time uploading these things. So it's 20% extra, 30% extra upload time is something that, by default it does not happen. Definitely want to encourage. Really change that's possible. Maybe in 10 years' time. That's not but
how else do you define what noise?
Same with blanks. You don't see a blank sample from a method. People can report very small pieces.
But everything increases folder. Then you ask for run order as well. Because you go to run order, that's where blank it is as well. Then the QC will happen. So it's always extra information. I think also the technology is in such a stage where you can't avoid that. You have to be able to interpret the data.
There's also, like Chris mentioned, there's two types of challenges where there's the metabolites, the database, numeric storage for sharing, metabolic data, and there's the lab. For us, there's for bound to rules to save the raw data. We have these contracts that are custom. We have to save the data for 5 even up to 10 years. It's even then is metabolites storing raw data, which is without a good design and use.
It is just this requirement always adds the burden of submitting. I mean, you could say, so the run order is something that you can help in the study design. But obviously that's not the only factor. The biological side of study design lives currently in the not captured. And there are things that a new ISA system, for example, will improve on the data capture. Again, that's a different topic. But it always there's a balance between burden of how much you want to capture and how much is ease of sharing data. The more you increase the burden of sharing data, the less chance of it becomes, unless there is a community expression, journals.
One of the uses of sharing data is actually so people can use it maybe in different purposes. Yeah. At least who like that. And honestly, I think if I was taking data online from any study, if you have no QCs there, I probably wouldn't use it. So just I think it kills it there.
Well, then again, you could always contact the original maybe and say, you got your data, and now I know the details.
Yeah, and there is a bit of a chicken and egg problem. If you don't start collecting data ruthlessly, let's put it like that, even without being concerned about these issues that we're talking about, you never discover these things, even if they are trivial or obvious, like the QC issues. So I think we need to be prepared as a community to go through this initial phase where we say, okay, we've made a lot of mistakes, let's throw that away. The first 2 years are useless. But the fact that we've done it brought the community forward. The learning is very it happened in all areas. I know that right also.
But Chris, at the beginning, when you did your introduction, you said, do we have a problem? And I don't think we have a problem at all. All three of us have a problem. We don't have a problem at the moment, but everybody can see that it's definitely a problem in a few years' time. Yeah. And we start thinking about how to tackle that problem. But at the moment, I think there's very few studies which are so big that there is a real issue for metabolites to be uploaded. So everything
you just see this curve and you know where it's going to end.
Yes.
That's the important question is what people want to do with data. Does it have to be stored in more data? And if we still will everybody reprocess it themselves, or do they just want to process it? I think it will be both.
Well, we are. Yeah. We are already, including ourselves, going through all the studies deposited and seeing how to reprocess it. I think we're close to the submitter scale of it and parameter optimization and these things. So lots of useful stuff is going on. It would never have happened if we hadn't had this
Just before you start, if there's online question, please ask, because I don't want to leave you neglected online. If there's any question, just shout and interrupt me.
So, yeah, I think I'm representing the last lab, Metabolomics lab of today. I worked at the NMC, the Netherlands Metabolomics Center, from 2008 until 2013. I was away for a while, and then I came back a year and a half ago. Started on Cosmos. I'm a software developer. Not the details about chemistry and metabolomics, but I'll try to explain what we do in our lab as good as possible. I'll talk about how we got to where we are now, and what the future is, the platforms, the instruments, and the data, and some of the challenges that we encountered. Like I said, in 2008, they started the Netherlands Metabolomics Center. It was a big Dutch center or consortium of both public and private partners. And one of the biggest assets there was the DCL, the Demonstration and Competence Lab, which now also still the heart of the lab that we have in Leiden. In 2013, the DCL, after NMC more or less the funding ended and turned into a foundation, it was rebranded to Biomedical Facility Leiden. And just recently, 2 or 3 months ago, we joined efforts together with the group NPL, the Natural Products Lab, also in Leiden, and became the core facility for Metabolomics of Leiden University. These are the 2 groups, the BMFL, the biomedical, what it says is biomedical, and the other group is really natural products, secondary compounds, metabolites. They're still separate in a different building, but I believe next year we're going to migrate into one new hyper modern building. In the future, what it states on our website is that we have the ambition to develop analytical strategies and focus towards personalized health. Challenges that or topics that we encountered, what we're working on is miniaturization. Like it says, smaller volumes, same sensitivity. We want to have higher throughput. Quite a large facility, but a lot of it is done by hand. All the intermediate steps are checked and stopped. We want to involve matrices, and we're gonna be organoplates. We're gonna build a platform around it. This is something we developed in a spin-off company. I'm not sure if anybody can read that, but these are the platforms that we have. We're trying to work according to the ISO standards. Also, because of the ISO standards, we have defined how we handle data, data management, let's say. We have a large variety of platforms, but also a large variety of machines and vendors that we work with. Also, I think this is one of our biggest challenges when you come to data processing, data storage, and conversion between the formats. Also have comparable output. I think the data processing is quite similar to the others, except that the heat treatment is usually done, especially in the production lab, with the vendor software. It's usually suited best for the format of the file that come out of the machine, and conversion is always time-consuming. Data size grows. People don't know what to do with it anymore. Don't trust it, or see that the open source products often change, and like I say, sometimes don't trust it anymore. We do have a software package that we developed in-house called MC Extract, which is still, I think, pending publication, but it is a new way of doing deep extract, LCMS. We also have the MZ Quality, a pipeline tool that we developed over the last 5-6 years to, by using the quality controls, the planning system stability tests that we have, due to, with the help of statistical methods and algorithms, we define the quality of the data and try to filter out the useful parts. And very recently, we decided, because this is one of the issues we did have, the price of the online storage, let's say, that we have at the university was rising. They wanted to have more for less. And that made us think that we don't need every file of every project on online storage. So we decided to start archiving things to tape, which works very well. It also compresses by default. Yeah, well, our challenge is like I think also all of us saying we don't have a real problem. I think the 50 terabytes, I think still handle we can still handle it. The 50 terabytes a year. We think it's going to grow until 60 to 80 terabytes per year, but not very dramatic. But the challenge is to handle all the different large data varieties and have it comparable, but also I have people coming to my desk and say, well, I have this data coming from this water machine, which I want to look in ProFinder or Agilent. And I think, well, that's not going to happen. Like, yeah, but I like that software better because, yeah, sorry. It's the different tools. We also have a lot of old machines with Windows 95 or 98 running because of that machine on that thing just works and nobody can touch it anymore. And so I think there we can improve. And yeah, automation might throughput. We want to do more samples. We now do about 15,000 profiles per year sample. But we do more. We have a lot of machines there. I think that was it. That's Lay University.
Good discussions. We are almost in time. There are other questions for this one.
I think the biggest difference, what I heard from the others, is that we do a lot with the vendor software. We don't convert it straight away to other formats to do the open source. Yeah. One of the this week I talked to the head of the lab and I said to her, well, what is like your main concern about data size and data sharing? And one of the things he said, well, all the different formats and conversions that you do also have copies of the same data eventually. So it would be better just to start sharing the raw data. But again, the company with the information needed to be able to interpret that raw data. But that also means that others should be able to access the vendors and where to be able to look at the files. So if you don't have a machine, that would be something.
Well, I mean, essentially, Metabolomics, we are in the same situation. In the lack of versatile open data formats in all the areas of Metabolomics, we need to just go the pragmatic way and store the vendor file, even though we know that the majority of our users out there cannot use it or need to maybe convert it with less than optimal solutions. Yeah, for data formats. And it's part of it. I mean, we were hoping that we would solve this in Cosmos, but things were going much slower than expected. And I guess the technology is moving much faster at the moment than the community can convert the data formats. But I think we are going to get there at some point. We've made this, what's the word? We promised in our grant proposals that eventually everything will be available for data.
But it's not only the software you need to look at the data, but for instance, if you work with semi-commercial systems or commercial systems like biography, there's a platform, intermediate platform that processes the data from what's so you can still have be able to see the original data, but if you don't have the biography set up to process the data, you can't see how the data can process from the original format to the result table.
And I guess they consider this part of their intellectual property.
And the same thing would be that if you have your sample analyzed in a commercial platform like Metabolomics, I don't think they just having the raw data, is interesting, but it's very limited. You can't reproduce what they can do.
Currently, most platforms to be compared, most data format, even GC can cover. But the community pickup on it is quite small, low as well. I mean, we try this by raising hand and looking at how many people actually do it. If you don't get, every response that everyone gets, you won't convert it. But the flavor, the software is very, very. So even if its tools are perfect, adoption are not necessarily the same.
It's not even, consideration just for events. One of the three things is, so we want to provide data sets, more data as well. That's fascinating, so we can but then we use a proprietary so they can then find it very difficult to reproduce the work unless we transmit two full image pieces. And because there's no way to go back from here to the style data, people get frustrated when they can't fully work.
Which makes another nice case for open algorithms, open data, source, everything needs to be free and open in science. And with this, maybe we could move to the coffee break and this after break.
Yeah.
Oh, I know, but I wish it would have right.
I haven't seen anybody
had 10 coffees.
I was going to say, Jake, you were the only one. You were the only two people said you ever raised your hand in Japan. And he said, "Who's using open?" You remember? I think it was two of you were raised your hand, and the rest were sitting there. Whether they didn't understand the question or they in Japan they were shy to say it wasn't me. But this year, same thing in San Francisco. The same question was asked by Stefan. You were there or not?
No, it wasn't.
You didn't play San Francisco. So you asked the same question, and number tripled. Really? So it is. I think it's like one thing we get.
I don't know how it works for the week of it's not perfect for some of the formats. But well, it's much better than what we used to do. But I don't know exactly how.
I think it's clear that people who are project don't regularly deal with water instincts.
That's a plus.
Because one problem we often find is the way that it handles the water usually gets a lot less function. Just trips everything.
I think so.
And so the event manager
So you know what? Because we asked an email a couple of us, and they said, "Oh, they will do it," and still the log mass is not there.
Yeah.
I would think if hear from you guys in Britain saying that, yeah, it's trivial, but it's a burden for other people that are tools, right?
Oh yeah, we should have actually.
It's a shame. This is so non-technician. This is worse than
Yeah.
because they removed most of it already.
There's some kind of interference between one wave and another wave. So yeah, that's what yeah, and the rest of the building. Yeah, started to boil too hot.
So much.
Yeah, so is there.
What phenomenon?
So essentially, like say, let's say your scope, so this time it's real data, linear genomics data, representation, not just coordination actions.
Does you mean, yeah, no, yeah, I mean, yeah, so we're just starting to like all people expect it to be up and running, the project's designed. That you have these types of all these real scientific you at the same time you're engineering the whole system to do all the process, but you have to do it at the same time. Results respected again. But it's 3 years. I mean, you don't do it, but you really need to build it.
We have to do it this.
No, you can, but you can't do it at full scale.
True.
You want to pilot. It's just that
I think, well, I'm not expecting anything to be reasonably complete. Absolutely. And then I think is that an operation
So one level is one. Okay, so it does think so that's okay, so one level up for you that's yeah. So S was the definite source of this information. But you cannot, in this case, there was you've probably seen the problem that you yeah, I remember it was last year. So yeah. No, I didn't. Yeah, I did see it, but I thought that's the thing is because we're in infrastructure, we're doing several different what we do is we need some infrastructure. So a lot of the pitching in that is very clear. Pitching in as a infrastructure stuff. So yeah, maybe we should. I guess what you want to do in your own terms as a boundary terms. Well, it's so easy. Yeah, easier. So this one, so we're sort of so it's actually the part of really part of this. Although there's no direct connection. Lots of the data resources, but also with there are probably people in there who are part of the screening world, open screen. Yeah. So okay, we used the Elixir. We talked a lot about Elixir. So that's good. They're much more fun to the company we work with some BDI to do. Certainly, but that's really Elixir.
So you're not sure what this data combination was looking at you seeing why you're not saying anything. Yes. Wait.
Yeah, that was the thing. So, yeah,
Yeah. You guys know. So, this guy.
Yes.
Yeah, no, I understood it. I understood it.
Cool, just in case.
We're
gonna go first.
I'm still talking to the purchasing committee, which is my wife, about the new Apple products.
Yeah, well, I made some mistakes.
Yeah, you're on the rest of the things as well.
Did the permissions issues? Why?
No, they're on the FTP side.
Do we have any backup system for the data?
Yes, but we need to note within a week.
Okay.
You learn more after a week. But this was, we told the guys to copy the files. So the missing files, they will be given to us.
So, welcome back to this second part. I've opened the windows because it's quite a bit stuffy. If you feel that's getting too windy or so or too noisy, just feel free to get up and close the window that disturbs you. Otherwise, it's good to have a bit of fresh air. As everywhere in this institute, heating and regulation of temperature seems to be a big miracle, and so we have to live with those windows while the system is trying to fight against the cold air coming in. Heating it up, yeah.
Yes.
So I'm handing over to
Yeah.
you swapped.
Yeah, because
And you don't want just the whole of it.
Just in case I say something. Casting will be shown.
Yeah, but that's only to people online, so that's not possible.
So we're gonna start now.